So we were talking about the criteria for the setting process of a wind farm. So first we said we should select the appropriate location in order to satisfy several conditions. First, we should have high wind velocities. We should have enough space because we need a large number of wind turbines. Third, we should select a zone that is far from population. Now, another criteria that is important is we should try to have the farm close to the power grid because larger is the distance between the farm and the power grid. You will need a large length of transmission, which will lead to a lot of losses. Okay, so to reduce the losses due to transmission lines, we can try to build the wind farm close to the power grid. And of course, as we have said previously, we should see if we should study the wind pattern in this zone. So it's not enough if you want to have high wind velocities during a certain limited period. We should have continuity. So we should try to follow. In general, we study we study the variation of wind for at least, let's say, 2-3 years to see if we have consistency, if we have annual wind present, so if it is available over the whole year and how it's varying with the seasons. So we should study the wind pattern over a complete year, and we don't just study 1 year because we want to make sure that it will be repeated. So we should study over a certain number of years to make sure that the wind pattern with time is good for the wind farm. And of course, the type of weather is very important. So we need to have high wind velocities, but let's say maybe we don't want to have, let's say, a lot of snow because this might lead to a destruction of the turbine. So if you have very hard conditions, this might destroy the blades. Okay, so we should also look at the weather. So how is the weather in this one? Now, what are the best sites for location? One of the best sites are hilltops, open plains, mountain passes, coasts, and offshore. So all of these are wide locations, okay, where wind is available. And it is best to build a wind farm where wind speed and direction has been studied for at least 1 to 3 years, and the strong and steady winds are needed to produce reliable electricity. So the site should not be prone, and of course, the site should not be prone to hurricanes and tornadoes to not destroy our wind turbines. Now, what about offshore wind farms? So we have farms that are constructed offshore. Of the advantage of offshore is that the space is very large, so we can easily find the uh, convenient locations to build wind farms. But what is little bit complex is that we need to have transmission lines underwater. So this might be a disadvantage. So many developers would like to move wind farms offshore because the wind are faster, smoother, and they can be close to major population centers on the coast. So these are the main advantages of using offshore winds. But as we said, major complaints about offshore are related to first visual impact and navigation impact. So we need to construct transmission lines underwater. So we know that the access to the electrical grid is very important, and offshore wind farms needs undersea cables to land, and maintenance and installation costs are higher than onshore. Now, we know that the wind pattern will vary annually, okay? But this variation, will be, this is why we should study this variation before deciding to design a farm in that location. But as you can see here, for example, it's true that we have variation of wind, but if you have this variation يعني, are still acceptable يعني, you don't have very large variation. So you can when you study 2 to 3 years, you can see if the wind availability is enough or not. Okay, so as you can see, they will fluctuate below and above the average, but the fluctuations are acceptable and you don't have, for example, a drastic change in wind pattern. So average annual wind speeds may vary in a percentage nearly to up to 25% from year to year, which is acceptable. So if we studied over 2 3 years and it seems fine for us, so we can consider that the design can be done. And of course, the wind variation is not only per year, but per day. So each day we have a new pattern. Wind varies daily, not only because of weather, but because of convective heating. So as we said before, we have several causes for wind variation. We have the conditions of weather and also the convective heating, which will create wind patterns. And the winds typically is strongest in mid-late afternoon. Convective heating is less of an influence in winter. Why? Because the weather effect will be dominant. So when storms dominate wind patterns. Now, in order to assess the effect of wind variability, we should yes, we should study the variation of wind before setting our design. And based on this, we can, based on the variation of wind, we can compute what is the power that can be produced with time. So as you can see here, for example, we represent the variation of megawatts that can be produced due to the variation of wind. So when wind is variable, of course, the production will be variable. So using wind power alone would require alternative generating capacity when the wind is not blowing, because at the end, what we will deliver to the population is not a variable power. Okay, we should produce a constant power. So since we know that wind might not always satisfy our needs, we can use with it another source. And in this way, that when we have low wind speeds or when we have low wind production, we can compensate using the other source. So the load demand can vary by 0.75 gigawatts, about a mean of 2.75 gigawatts. Additional demand could be easily provided by stored wind power or with good interconnectivity to the grid for power balancing. And of course, sometimes wind is more than needed. So when wind is more than needed, we can store energy and then use it when required. So this is also another strategy if you don't want to use another technique. If you want to use, if you don't want to use fossil fuels, or if you don't want to use in parallel solar or any renewable energy, we can rely on wind. But the condition is that we should have sometimes excess of wind power, so that we store it to give it when we have when no wind is blowing or when the velocity of wind is relatively low. So connecting wind farms together over large areas will help a lot into smoothing the variations in supply and errors in the wind forecast. So this is also a very important idea. So if we can connect several wind farms, this will reduce a lot the fluctuations, because let's say one farm is having a lot of excess of power and another one needs power, so they can compensate each other. And in this way, we can build a certain connection between farms that will ensure a constant power output. Now, what about the transmission problems? So it is very important when we design a wind farm to know how we will transmit electricity, because this will need a preliminary design to achieve a good answer. Because you know that when we want to build the transmission lines, we should look at several criteria. So we should ask ourselves the following question: where is the wind? So where wind is better, and where are the population centers? because we should be far from the population centers, but at the same time not very far from the grid, from the electricity grid. So where are the wind farms, and how do we get wind energy from the wind farms for the population centers? So as we said, we should look always at an optimal design between the location of the grid, the electricity grid, the location of the wind farm, and the population location. Okay, so we should be far from the population location, but at the same time, we should be as much close as possible to the electricity grid to reduce the need for construction of transmission lines.
Miss, and to reduce as well the voltage drop in the transmission lines.
Yes, of course. Because larger is the distance, larger will be the voltage drop. So, for the wind turbine design concept, as we have talked before, the materials of the turbine blades are very important, and we have a lot of research going on in this field. So, in general, for the blades, we use composite materials as carbon fiber, fiberglass, which are characterized by low density and high strength and stiffness. Because as we have seen, the blades should have very important mechanical properties to resist the continuous action of wind. So when we talk about fatigue, it's we are submitting a certain object to repeated cycle of load. So it's not only the issue of high load. So you can apply a high load. The high load will lead to high, if you want, high mechanical constraint on your system. But plus, if you remove this load and you add it again, so if the same load you remove it and you put it again, you remove it and you put it again, this will cause what we call fatigue. Okay, because by this is a cyclic, so we are repeating a certain cycle of loads. This will lead to fatigues after a certain number of cycles. So fatigue properties of the materials used are important because of the large number of revolutions that a turbine makes. So in general, we construct a turbine for a 30-year lifetime. And for a 30-year lifetime, it will undergo nearly 10 to the power 8 rotations. So imagine the number. This is why it should be able to resist to the fatigue phenomena. So we should avoid fatigue failure. And to avoid fatigue failure, we should avoid fracture of the material and the initiation and growth of cracks under repeated cycles. So the mechanical properties of the material should be very high, at very high standards, in order to avoid fatigue due to the cyclical rotations. So rotation of the blades will cause the loads experienced by the turbine to change in a repeated way, which can weaken the structures. This is why we should use a material that have a high number of cycles before fatigue, because you know that I don't know if you have all taken material courses, but any material, okay, if you subject it to a repeated load, you can count a certain number of cycles above which it will lead to failure. So higher is the mechanical property of this material, then it can support a larger number. So for example, here we can use a material that can support, let's say, 10 to the power, 2 times 10 to the power 8 rotation. So if it can sustain 2 times 10 to the power 8 rotation before failure, then it can resist the 30-year lifetime of the wind turbine. Okay. Now, we have what is called also, when we design a wind turbine, we have the rated power. We define the rated power. The rated power represents the maximum power the turbine is designed to produce. Okay. So, but you know that we cannot have always constantly the maximum power, because the wind power is variable. So the maximum rated power will take place at the maximum wind velocity. But over the years, the wind velocity is variable. So we can calculate the rated power, and we can calculate an average power. Okay. So the rated power is the maximum power the turbine is designed to produce. And this maximum changed from 80 kilowatt in 1985 with a rotor diameter of 20 meters and a hub height of 30 meters to 5 megawatt in 2011. So you see the large increase from 80 kilowatt to 5 megawatt. And look, for the dimensions also, we have a lot of improvement because we moved from a diameter of 20 meters to nearly a diameter of 125 meters. So imagine how it's huge, this turbine. This is why the space needed is very large. Okay, and the height is up to 90 meters. And the increase of height is very important because when you increase the height, first, as we said before, all obstacles that you have will not be able to resist to wind motion. Okay, so in this way, the wind pattern can reach you in a very effective way, and this will lead to a better production of power. So in 2011, we reached hub height of 90 meters and blade diameter of 125 meters. Now, for the capacity factor, if you want, is defined as the average length. Okay, so let's say we said that the rated power, which is the maximum power, is calculated. The capacity factor represents, if you want, the percentage. We should multiply the rated power to obtain the average output power. So the average output power is equal to the rated power times the capacity factor. So when we say, for example, that the capacity power is 40%, this means that in average, we are producing 40% the maximum power of the wind turbine. Okay. So here we can see the improvement of technology with time. Okay, so you can see in this graph how with time the dimensions are increasing. We are looking at two main dimensions, which are the hub height, which is the distance between the foundation and the axis of the turbine, and the diameter of the wind turbine. So you can see the large increase with time, and we have given numbers in the previous slides. So the size of wind turbines has increased over the last 20 years. Typical specifications in 1985 were rated power 80 kilowatts and rotor diameter of 20 meter and hub height of 30 meters, while in 1995 the rated power reached 600 kilowatt, a diameter of 46 meter and a height of 50 meters. And in 2011 we reached 5 megawatt in power, a hub height of nearly 100 meters and a diameter of 125 meters. So this is a very large improvement. Now, the natural frequency of vibration of the tower lies below the rotational frequency of the blades. So what do we mean by this? You know that your turbine is fixed on a certain support, okay? And you have a certain vibration frequency for the tower. So this is your tower, the tower that is supporting your system, okay? You have a certain natural frequency of the tower, which is different than the frequency of rotation of the blade. And because the natural frequency of vibration of the tower is smaller than the rotational frequency of the blade, then when you start your turbine, you will pass by the natural frequency of vibration of the tower. So to avoid vibration of the tower, you should your change of speed should be very quick to avoid shaking the tower. Okay, why? Because when you put your turbine on, you have a certain transition zone. So you will go from a rotation of 0 to the maximum speed. Okay, so when moving from the rotation of 0 to omega max, which correspond to the maximum frequency, which correspond to frequency maximum, you will pass by a certain point, you will pass by the natural frequency of vibration of the tower. Okay, and to not have a lot of time on this frequency, you should have a quick startup, because if it's very quick, it will not have time to have vibration. Okay, so to avoid vibration of your tower, So this is the natural frequency of tower. So to avoid the vibration of tower, what you can do is to start up in a very quick way your turbine. Okay.
Natural frequency is the resonance, right?
Yes. At natural frequency, you have the resonance mechanism. Okay.
Okay.
So to avoid the resonance, what you do is, which will lead to shaking the tower, you will do this in a very quick way to not have enough time for your tower to reach resonance state. Okay.
Yes. Okay. Thank you.
Now, during electricity generation from wind, the wind turbine needs to be controlled to optimize its output. Okay, how we control the turbine? As we have seen before, we need to orient its blade in a way to optimize the rotation of the blades. And this can be achieved by the yaw control mechanism, which consists on a computer programming system. So what we want to do in this case, we will have inputs to the computer program. We will take as inputs the velocity of the wind, the direction of the wind, and based on calculation done by the computer program, we can select what should be the corresponding orientation of the blades in order to lead to optimized performance. So wind provides the driving torque for the electrical generator. The generated current is hence proportional to the applied torque. At constant rotational speed, the wind torque equals the generator torque. So when we want to measure the electricity output is proportional to the torque provided to the wind turbine. So larger is the torque provided by wind, larger will be the current that is provided. And when we reach, so here you can see this is a figure for the startup of our turbine. So if you want, when you increase your when you increase the speed, when you increase the wind speed over the turbine, you will increase the output power, okay, until reaching the maximum powers that you can take, which your turbine can take. So once you reach your maximum power, you will reach the maximum electricity output. Now, when setting a wind farm, developers must consider any possible wildlife impact. So as we have talked about before, birds, the problem mainly is with birds. So we try to design the height in a way to not be very harmful for the birds. So though this was not the case in early wind farm developments, today all proposed wind farm must undergo a strict environmental impact assessment. So, with time, the height of wind turbines is increasing. This is why it might become more harmful for birds. So, currently, and you know that with time, the environmental impact becomes more important. So, one of the primordial factors when designing a wind farm is to study its location and if it's a zone where we have migration of birds and at what height in general we have birds motion to avoid killing birds from wind turbines. So this is the chapter of wind energy. Okay. Next time, hopefully, we will start the chapter for solar energy. In this way, we covered the different renewable techniques. We have other renewable techniques, but these ones are the most widely used: solar energy, wind energy, hydropower. Okay. So next time we will introduce the solar energy and its application. Any question for this?
Yes, doctor, I have a question.
Yes.
How do the turbines affect each others in a single wind farm?
Yes, very important question. In general, we should put a certain enough space between them, okay, in order to not be not we don't want to have one turbine that is an obstacle for the other. Okay, so the spacing should be optimized in a way that wind can reach all of these turbines without interference between them. Okay,
Okay, thank you. Yes.
so this is another criteria. The spacing between turbines should be also studied in a convenient way, because if you put them very close to each other, this might affect the wind profile over the wind turbine. Okay.
So we need to space them so that the flow field will gain its strength, right? Because
Yes,
after it hits a turbine, we will get a value of U2, which you said is the smallest value of the velocity.
yes, exactly.
Okay.
Sorry, doctor.
Yes,
Regarding the A1 and A2
yes,
that you explained up,
yes.
ما كتير فهمت إنه شو هن هول الأرياز إنه
Okay, يلا, I will re-explain. Okay, look, you have a uniform flow. Okay, imagine that you don't have the turbine. You have a uniform jet that is coming. Okay, just 1 second, please. Okay, let me select. Okay, so this was your flow initially. Now, what will happen when you, whenever, in any case where you have a flow hitting a body, you will have separation. Okay, so you will have flow separation. So your streamline, if you want to draw streamlines, if you want, these are streamlines. And if you take a picture of you, if you do smoke generation and you take pictures, these are the vectors of velocity you will see. So your velocities are like this. Okay, so you can see how, due to the presence of the turbine, if you follow your streamlines, you will have like flow separation like this. And this will affect the zone just before and just after your turbine. So until establishing again a uniform motion at the end. Okay. So due to the presence of this turbine, you can have these two limiting streamlines, the upper one and the lower one. So if you observe your streamlines, you can see that the cross-sectional area of the flow is being increased as you go over your turbine. So, and you will reach finally to have again a flow that is in the horizontal direction. Okay, at the end you will establish a certain cross-sectional area, which is the maximum one at this level. Okay, so if you want, these cross-sectional areas are due to the streamlines of flow that are due to flow separation when going over the turbine. Okay, so if you do a small analysis, if you take a control volume of air in this, if this is your control volume for air, you can consider that this is my inlet here, and this is my outlet. You are a mechanical engineer?
Yes.
Okay. So if you want to find the interactive force between the turbine and the flow, you remember from fluids the linear momentum equation?
مش كتير بس
Okay, I will just repeat the idea. If you have in fluid flows, if you have a fluid passing over an object and you take as control volume the fluid, then you can write that the force of the object on the fluid, so the force F of object on the fluid, so I take the fluid as my control volume, is equal to the mass flow rate m dot times velocity out, u out, minus un. Okay, and by principle of action reaction, this force is equal to minus the force of the fluid on the object. Okay, So now what you are interested in is the force on the turbine, okay? Which is this one, minus F fluid on object, which will be equal to m dot un minus u out. Now how to compute this term? M dot is simply u0 a0 times rho, okay? So, and at the same time, it's equal to rho u1 a1 and rho u2 a2.
اوكي بس ال A0 يعني انه هو before the turbine كيف
هي
انه ما
الكروس
في
سكشنال اريا
bypass.
اذا بدك، الكروس سكشنال اريا يعني انت مش you draw these two streamlines. انت if you take picture of your flow you will see these two streamlines that are هيك عم ببعدوا عن بعض due to the presence of the turbine. اوكي يعني انت تخيل انه صورت اخذت picture للvelocity vectors او اذا عملت smoke generation then you can compute يعني you can see how the velocity vectors are varying. يعني اللي عم بيصير انه before التوربين كانوا parallel streamlines، كان عندك parallel streamlines for the flow but due to the presence of the turbine صار في deviation of the streamline فبلشوا يوسعوا، بلش توسع الكروس sectional area. اوكي after يعني very far from the turbine you can have a certain developed خلص بيرجعوا horizontal. اوكي بس وقت يرجعوا horizontal the corresponding cross sectional area A2 is higher than A1 واكيد كمان A1 is higher than A0. That's it. يعني A0
Okay, بس
A1 A2 are determined by the streamlines of flow over the turbine.
اوكي بس بال A0 انه before the turbine مش انه ما في هواء outside of the A0 انه في هواء وين ما كان المفروض before the turbine. لا
هلا اكيد في هواء وين ما كان بس انت بدك الهواء يلي اثر على التوربين مزبوط.
اوكي يعني اللي برات ال A0 ما بيأثر عليه
لا
على التوربين.
لا
اوكي جي thank you.
Okay. Any other question?
No, thank you.
Doctor?
Thank you.
Yes.
How does climate change affect the capacity of the wind energy over the years?
Yes. هلا الكاباسيتي فاكتور هو مثل average صح؟ and if you have weather a lot of variation كل ما الويند يعني صغر عن الماكسيموم then the average will be reduced if you want. Okay, so if you have very large variation of your wind انت بيهمك ال average value. If the average wind is varying then the capacity factor will vary. لأنه ال capacity factor if you want هو فينا نقول انه ال average power is equal to the maximum power times the capacity factor CP. Okay, so this capacity factor will be affected by the average power يعني which is related to the average wind velocity. يعني انت ال weather variation حيأثر على ال average wind velocity which will affect the average power and then will affect the capacity factor.
Okay, so are there any predictions if it will increase or decrease due to climate change?
Of course, if the wind velocity is increasing due to climate change, then CP will increase. And if the wind energy will decrease due to the climatic change, it will decrease. And it will follow the variation of wind average velocity.
Okay, thank you.
Any other question?
I have a question, Doctor.
Yes.
In designing of wind power system on offshore wind power system.
Yes.
So what is the effect on the water body?
Yes. The effect on water body, yes. First, you can have, if you want, you need to build foundation undersea, and this might cause if you want if you have some vibration. We can avoid vibration as we said by the quick startup, but if we have vibration, it will lead, if you want, to formation of waves in water. This is one effect. But plus you need to build the transmission lines undersea which also is of high cost and is technically difficult. More than this, you don't have a lot of disadvantages other than that, and it's not harmful. Okay, but you need a large space, and this might, if you want, affect the circulation of boats in these zones. So you should not have maybe circulation of boats in these zones. Okay. Any other question? Okay, so see you next time. Bye.
Doctor, a question regarding the session. Anna, but regarding the project, do you have a minimum number of pages for the report?
No.
You know, how many pages do you expect it to be?
Yani at least if you want for any good paper, let's say not less than 30.
Okay, thank you, doctor.
Okay. Well.